Hey guys, for calculus, this is 4.0, Introduction to Integration and Riemann Sums. This is not a lesson that you usually find in the calculus textbook. This is one that I like to add because this content is on the AP and it kind of gives you a nice little leeway to understanding what the whole idea behind integration is and the concept of it is. All right, so to begin with, integration, also known as anti-differentiation. I know it's a big word, but we see the word differentiation, which means derivative, and anti is the antithesis of it. It's to undo it. So it is literally the reverse process of doing differentiation, of doing the derivative. This is a mathematical process we're going to be doing when we're solving. We're not going to see much of that today. Just want to break it down for you. So the same way before, to undo a positive 3, you would subtract the 3. That would be the inverse operation. Integration, anti-differentiation, is the inverse operation of a derivative. Now, why do we need integration? Okay, integration is also known as finding the accumulation of something. Okay, it's us solving for total amounts, and that's what we're going to see more in the applications. In the AP test, this is mainly like word problems and the free response questions at the end. And in those word problems, the wording that we're going to be seeing, because it's asking for total amounts, is how much did they have? How far did they go? What was the total amount of? How many did they get? So let's look at just this very elementary level question just to connect the dots with the concept, okay? It says a ship moves at a steady rate of 7.5 miles per hour from 7 a.m. all the way to 9 a.m., okay? So this boat only went 7.5 miles each hour from 7 to 9, okay? What is the total distance traveled by this ship? Well, if he went 7.5 miles for 1 hour and then for a second, we could see that we could just multiply 7.5 times those 2 hours, and we get that he traveled a total of 15 miles. Okay, very basic, right? What I want to draw a conclusion to you now is that if you draw the shape that's underneath this function and you find the area of it, you are literally doing the same thing. The base was your change in x, right? I changed 2 different hours from here to here, right? In math, our change in x, we call that our delta, because delta means change. So our change in x was 2, and then our height, right, our y value was at 7.5. So you're going to also hear us saying that integration is also known as the area under a curve. In this case, we went a very elementary, so we didn't have a curve. We had a linear function. But in order to find this total amount, this integration, visually on a graph, we are finding the area under a curve. Now, let's brainstorm for a minute. Let's reanalyze this question. Because in reality, when you're on a boat, if you're in the Florida Keys, you're not going 7.5 miles the entire time you're on this boat, right? Let's say at 7 a.m. you take off from your dock, you're not moving, so you're at 0 miles per hour. You start accelerating, right? You end up at 7.5 miles an hour. And then maybe you speed up to catch, that winds, and then you start slowing down, and then maybe you pick up your pace again. You slow down all the way till you get to your destination and you come to a complete stop and you're going 0. Okay? So if we take this concept of area under a curve, I'm going to use a pencil just because I'm going to keep erasing as we brainstorm. If we do area under this curve, if we do base times height like we did over here, notice that we're going to have some room for error, right? When we do the base times height, we're going to get this space here in our area, which is going to be a value that we didn't get. We're going to be missing this quantity. We're going to be getting extra amounts here that we didn't do, and then we're going to be missing this value. So notice, oh, and here too, we're going to be getting an extra amount in our base times height here that we didn't actually do. And that is why using just base times height is going to be giving me an estimation, okay? So the question is, how can I start to get a better estimation, Okay, well, this old guy, really, really long time ago, his name was Riemann, he started to analyze, well, if instead of doing one rectangle for base times height, if I start to do multiple of them, I can get a better estimation. So he said, okay, maybe if here I do a small rectangle, and then here I go a little higher, here I go a little bit more, and I go a little higher. You notice that that room of error that we started to see starts to become a little smaller. Maybe this time I'll go over, right? And so on with these rectangles, okay? So Riemann kept thinking, okay, I'm getting better, but I'm still having these little error spaces. What can I do to start getting a better exact estimation? Or even better, to get an exact value? Well, Riemann concluded that if I keep putting, the more rectangles I put, the smaller this error space starts to become. So if we think back to the beginning of calculus when we started learning limits and we talked about infinity, he said if I could technically start getting closer and closer to an infinite amount of rectangles, the closer and closer my answer is going to be to the exact value. Okay? So hold that thought on infinity and putting multiple rectangles. That's going to come into play when we take what Riemann discovered and connect it over to integration. One more thought down here before we keep talking about Riemann. We said that integration graphically is the area under a curve. So we said length times width or base times height. We made the connection on a graph that is the x times the y. Another way of saying y is f of x. I'm going to explain this little notation with a little sub I here in a moment. We said that x, like over here, the total x's was the change that happened. So they can call that delta x. And then another notation you're going to see is just the f of x, and instead of a delta sign, they put the letter d. I just want you to start getting used to these two notations because we're about to see a lot of it. Let's talk about Riemann's sums a little bit. Now, the guy's name was Riemann. It's called sums because he started taking the area of all of these rectangles, and the sum means to add. He started adding them together to get that total area under the curve. So a formal definition of Riemann's sums is a method of approximating an integral, which is the area underneath the curve, by dividing up the region into a bunch of subintervals, meaning all those little rectangles, and then finding the sum of their areas. So you find the area of each of those rectangles and you add them up. And again, the more rectangles you do, the closer to the exact answer. So again, I told you Riemann started to think of getting an infinite amount of rectangles. Okay, keep that infinity in your mind as we talk about the notation coming up. So again, Riemann's sum was an estimation that led us to integrals, the exact area under the curve. This notation here is going to be coming up next video, next section of the actual mathematical procedure, the anti-differentiation we were talking about, where Riemann's sum, I want you to think back in the beginning when we learned derivatives and we learned the limit definition of a derivative. Riemann is going to give us a limit definition of an integral. So this is going to be the estimation, and this is going to be the exact value. Okay? Good news is, guys, in the AP test, they do not make you solve using the limit definition for either derivatives or integrals. But what they do make you do is recognize the limit definition, convert it to the integral, and then use our rules and our shortcuts. Okay? So right now what I'm going to show you is both of these notations and how to convert so that you can solve the shorter way on an AP test. Okay? So Riemann's sum says the limit as n approaches infinity, the sum of n intervals, so n amount of rectangles, we want to get as close as possible to an infinite amount of rectangles. And we're going to add multiplying the base delta x times the height. Okay? Now, an integral is just a different notation. This is going to be the shortcut. F is the y, delta x is the x, so base times height. And then this S stands for sum. Okay, here's the Greek letter and here's the Roman letter, just two different guys coming up with different notations. From A to B, meaning from the furthest x to the left to the x to the right. Okay? And then these two are going to be very important for converting, where delta x is found when we convert by doing b minus a divided by n, and x sub I is a plus delta x sub I. Okay? This is a lot of letters, lots of variables. It seems so much more confusing than it is. Wait till we convert and you're going to see it's not that bad. Let me refresh you on a few of these other symbols to remember. You might have seen them in previous classes. That capital E there, it's a Greek letter that means sum. The n is the number of intervals. Remember, we want to get close to an infinite amount of intervals. Those intervals are those rectangles. That little I is a variable to determine not all x's in the graph, but a specific x. That triangle with the x is delta x, my change in x. The x sub I is the right x value of a rectangle. And then the x sub I minus 1 is the left side. And that's going to come in handy more when I start showing you the different types of estimations that Riemann solved for. Okay? So let's check this out and let's start converting. Okay? We're going to do two examples. The first one, we're going to go from Riemann sum to integration. And then the next one, we're going to go from integration to Riemann sum. Okay? So if Riemann sum is written like this, I see two things being multiplied, right? I see something being multiplied here by something here. And if I look at my notation, I have my f of x times my delta x, which means that this guy right here must be my delta x. And all of this is my f of x sub I. Okay? Meaning that whatever is inside the function in parentheses is my x sub I, which means this is my x sub I. Okay? So now, from my x sub I know that the first number is my a. So I know that that guy right there is my a. So far, I know that a is 2. I also know that delta x, which is b minus a over n, is equal to 3 over n, because I said this was delta x. And if I already know my a, I can move on to say that b minus 2 over n equals 3 over n, right? All I do is plug in that a in there. And so if I have n on both denominators, I can cancel them out, multiply one to the other side. And now I'm working with b minus 2 equals 3. Add the 2. And I know that b is 5. Okay, so if I'm converting to an integral notation, I have my big fancy s. I know that my a, which goes down here, is 2. And my b, which goes up here, is 5. And then I want my f of x without the sub I. So that means I'm going to plug an x where that x sub I is. So if all of this is x sub I, I'm going to say 3. Replace the x sub I with just an x. So replace all of this with just an x. Keep writing the function, plus 1. And instead of writing delta x, I'm going to write dx. And I'm done converting. Okay? So hopefully not too bad. As long as you can pinpoint what's what, you can rewrite it. And then starting next lesson, we're going to start learning those shortcuts. Okay? Let's look at the next one. Okay? Now I'm working the other way around. Now they gave me my a, they gave me my b, and they gave me my f of x, and this is going to become my delta x. Okay? So, step 1, if a is 5 and b is 7, now I can solve for delta x, which is b minus a over n. So I can say 7 minus 5 over n, which gives me 2 over n. Okay, all I did was find my delta x. Let's start writing the notation, okay? My notation is to write the limit as n approaches infinity. All of this portion right here stays the same. This is what I'm going to start switching up. So limit as n approaches infinity, the sum from 1 to n. And now my function, I need to plug in an x sub I. X sub I is a plus delta x sub I. So that means x sub I, if it's a plus delta x sub I, is going to become, a was 5, plus delta x is 2 over n, and then sub I. Okay, so now my function, if it was x cubed plus 1, I'm going to replace that x with the x sub I. Okay, so my function is x cubed, so instead of x, I'm going to put my x sub I. And that's the x, so now I need to keep writing the cubed and the plus 1. And then instead of dx, I'm just going to write delta x, which we said that delta x was 2 over n. And now I'm done. So the next kind of questions you can see involving Riemann sums is that Riemann determined that as he was doing his estimations, there were different ways to estimate according to a graph, an equation, and a chart. So I'm going to show you the different methods that he determined, and I'm going to show you them with a graph, an equation, and then a chart. So first, graphs. He determined that this, remember, we said rectangles, base times height. He can do the rectangles according to the right height of the function. So if this is my curve, my function, we're going to say that n, my number of intervals, is going to be 2. Okay? So we want to be able to estimate using Riemann sums the area under the curve, the integral from 0 to 12. And if n is 2, that means each interval is going to have a delta x, a change of 2. Okay? So with a right Riemann sum, he's going to pick the height of the rectangle according to the right side. So if it's a distance of 2, my height according to my left would be right here, but my height of the function according to the right would be all the way up here. So you can see every 2 numbers, I did a rectangle according to the height of the right side of the function. That's going to determine my y value when I do base times height for each of these rectangles. Okay, the first one was right. Then the next one we'll do is according to the left. Notice that I have an underestimation here because I have all of this gap. These two give me overestimations, over, underestimation, under. Okay, so notice that the left and the right Riemann sum aren't too accurate, right? But they are going to give us an estimation. Now, the next one he found, which was most accurate, is the trapezoid. A trapezoid is when you have 2 different heights. So he used both of the heights from the left and the right, and then drew a line diagonally, drawing a trapezoid. Notice that I do have mostly underestimations, but what I'm missing is so minimal in comparison to these, okay? And then the last one that we're going to see is midpoint, which he started to pick the height, not off of the left or the right, but by the middle number is where he picked the height, okay? Now, what I've written for you here in black, do not stress this part. These are just notations. But they are not even found on the AP exam. I'm going to show you how this is asked, okay? So for this first question, if it asks to estimate the area under this curve according to a right Riemann sum, and they wanted my n, my distance between my delta x to be 2. Sorry, I just noticed I put an n equals 2. I wanted it to say delta x equals 2. All right, so my change in x, my delta x is 2. That means I'm going to say, okay, the area, the whole point of Riemann sum is to add up the area of each of these rectangles. So my first one is going to be base times height. So base is 2 times my height, according to the right, is 9. I'm going to add it with the next one. Plus base of 2 and my height according to the right is 7. Move on to the next one. My base is 2. My height according to the right is 3. Next one, my base is 2. My height according to the right is 2. Next one, my base is 2. My height according to the right is 4. And on the last one, my base is 2, and my height according to the right is 8. Okay, now that's a lot of arithmetic there. If you notice, whenever in a Riemann sum, the base is the same throughout the entire question, then I can just factor it out and say 2 times, I'm factoring out all of these 2's, and what I'm left with is 9 plus 7 plus 3 plus 2 plus 4 and plus 8. Notice I put an approximation sign because the whole point of a Riemann sum is to estimate the area under the curve according to the right. That's just notation right there. And when you solve this, you end up getting 66 units as an estimation of the area under the curve. Okay? Let's go ahead and do the same thing with a left Riemann sum. The only difference now is I'm picking my y values, my heights, according to the left side of this triangle. So if you catch that all of them are going to have a delta x, a base of 2, you can factor it off in the beginning, but I will go ahead and do it initially without that step. So my first height is 3, base of 2, my next height is 9, right? And then my next one, base of 2, my height is 7. The fourth one, my base is 2, my height is 3. Okay? My next one, my base is 2, my height is 2. And my last one, my base is 2, and my height is 4. Okay? So again, just picking the heights based off of the left, I can factor out a 2 and say 3 plus 9 plus 7 plus 3 plus 4. Plus 2 plus 4 is the last one. And when you solve that, you get 56. So notice this one was like even lower than this one. I think our trapezoid, our next one, is going to give us an estimation as to who's closer to the actual answer. Okay? For my trapezoid, okay, you need to remember the area of a trapezoid. Okay? If a trapezoid is standing up, the heights on either side are different, which means you have to take the average of the heights and then multiply it by the base. If your trapezoid were sideways, then the bases would be different, and you'd be taking the average of the base and multiplying it by the height. So, okay, average of the heights for this first one. This one's a little lengthier, okay, guys? I have a height of 3 here, and then a height of 9. So I have 3 plus 9, and then I'm taking the average of it. That's going to be my height, and then times my base, which is 2. Okay? Same thing for the next one. Average of my heights, I have a height of 9 and 7, times the base, which is 2. Next one, average of the heights. I have 7 and I have 3 times the base, which is 2. Next one, average of the heights. I have 3 and 2 times the base, which is 2. Okay. Next one, average of the heights. I have a 2 and a 4. Times the base, which is 2. And my last one, I have a height of 4 and a height of 8. Take the average. Now, a really nice thing, when my base is 2, it's going to cancel out with all these denominators, okay? If not, I could factor out a 2 from all of them and factor out a 1/2 from all of them, and then just add all these numbers, okay? So all of my denominators are 2, and my delta x, my x is 2. They cancel. So I want you to see what happens here. I'm going to scoot over. I don't know if I'm going to have room. Every time you do a Riemann sum according to a trapezoid, watch what's going to happen. I'm going to have the first number 3, and then plus 9, plus 9, plus 7. Now the next one plus 7, plus 3. The next one plus 3, coming down here, plus 2. The next one plus 2, plus 4. And the last one plus 4, plus 8. Every single time you do a Riemann sum for trapezoid, you're going to have the first number 3, right? Whatever it may be. Here's 3. And the last one 8. And then notice, because I'm using this height for this trapezoid and this trapezoid, all of these numbers get written twice. That will happen every single time. And when you add those up, I get 61. And visually, you can see that's a much better estimation. And it's even in between the last 2 answers we had. All right? Let's check out our last one here. Midpoint sum. So the whole point of a midpoint, again, is that you are picking the height based off of the middle x. Okay? So if my middle x in between 0 and 2 is 1, I'm going to go up at 1 and pick my height, which in this case would be 7. Okay? So area according to midpoint, my base is 2. My height, we said, is 7 at the middle. Next one, my base is 2, and my height according to the middle here is 9. Next one, my base is 2. My height according to the middle is 5. Next one, base is 2. My height according to the middle ends up in between. So I'd say it's about 2.5. The next one is the exact same. Base of 2, height of 2.5. And my last one, base is 2, height, we'll say that's at 5. Okay, again, I have all those 2's in common. I can factor that out. And now I'm left with 7 plus 9 plus 5 plus 2.5 plus 2.5 and plus 5. Solve that and you get an estimation of 62. So believe it or not, midpoint is actually a really good estimation as well, because every time I'm under, because it's midpoint, I'll also end up having an under. So underestimation here, I'm missing this, and here I'm also having an overestimation, and they kind of balance each other out. Notice how close that was to the trapezoid answer, okay? All right, so now we're going to see Riemann sums using equations and charts. These examples say approximate the area under the curve over the interval using 4, and each of them will do different versions, okay? Keyword here is the word approximate. That lets me know that I'm not doing an actual integral. Approximation is always Riemann sum. Under the curve also, it lets me know that I'm doing the approximation of an integral. And then they're going to give me 4 intervals, which means there's only going to be 4 rectangles for each of these questions. A is going to be a left endpoint Riemann sum, okay? So the first thing I'm going to do is create my chart, okay? Here's my function and here's my domain. Here's from the furthest x's that they want me to do. So for my x's, I'm going to go from -4, and if delta x is, well, actually, delta x is what we have to find. If I have 4 different subintervals, earlier in the video, I told you that n is how many subintervals they want. So that means that delta x is equal to b minus a over n. And they wanted n, the amount of subintervals, to be 4. So that leaves me with 8 over 4, which gives me 2. So that means every time I write a new x, they want me to go 2 numbers over. So from -4, I go to -2, then to 0, then to 2, and then to 4. Okay? Now the next thing I need on this chart are my y values. So all I'm going to do is plug in -4 in here. If you plug in a -4, you get 10. If I plug in a -2 here, I get a 4. If I plug in a 0, this cancels and I just have 2. And because this is squared, plugging in a -2 squared and plugging in a +2 squared is going to give me the same thing. Same thing with the 4. Okay? Now, with your chart and maybe a different color pen, I want you to draw your 4 rectangles, right? So here's my first rectangle. Here's my second. Here's my third. And here's my fourth. Okay? If you looked at the graph that we did just before this question, these would have been the heights at each end of the rectangle. Okay? Because my y value is my height. Now, because this question is specifically asking for a left endpoint, I'm going to use the left height. So for this rectangle, I'm going to use 10 as my height. For this rectangle, I'm going to use 4. For this rectangle, I'm going to use 2. And for this rectangle, I'm going to use 4. So this is the only number that is not going to get used. Okay? So when I go to find my area according to a right rectangle. Why did I put right? We're doing left. Crazy me. We're doing left. I apologize. Okay? That means, remember how in the last questions, since delta x is the same every time, I can factor it out and leave it out front. I do not have to write it every single time. And now I'm just going to have all of my left heights, which is 10 plus 4 plus 2 plus 4. Okay? Once I clean that out, I get 42 and I am done. If you are taking an AP test, I encourage you, and if you were my student, I wouldn't allow you to go past this. Free responses get left just like this. Do not waste your time, energy, and the chance of making a mistake doing your addition and multiplication. You only have to go to this last step if it is a multiple choice question. Okay? Let's go on to the next one. Right endpoint is what we're going to do next. Okay? So let's find our delta x for this one. So we have b minus a over n. I'm keeping the same exact n as the last question, which was 4. And that leaves me with 4 over 4. So my delta x is 1. So when I create my chart, I'm going to start at -3, and I'm only going to go 1 number over. Okay? Now I'm going to get my y's just by plugging these x's into this equation. Okay? So now that I know my y values, I'm going to draw my rectangles, right? First rectangle, second, third, and this question said we should have a total of 4, and we do. Now, because we are using right endpoint rectangles, for this rectangle, I'm going to use the right height, which is 8. For this one, the right height, which is 11. For this rectangle, the right height, which is 12. And for this rectangle, the right height, which is 11. Which means we do not end up using this 3. So now, for my area approximation according to the right, it is delta x times each of my heights. So I'm going to factor the 1 out to the front. 1 times anything is going to be itself anyways. And I'm going to add up my different heights. So I have 8 plus 11 plus 12 plus 11. And this gives me 40. Oh my goodness, I had added wrong on the last one. Look at me. I apologize. This should have given me 40. Just looking at my answer key and caught myself. All right. Sorry about that. So a little quick detail on notation. Notice that both times I put an approximation symbol. As long as you put the approximation symbol at the beginning, you do not have to put it after, because all you're saying is that this is equal to 40 and 42, but they are an approximation of the area under the curve according to the left or the right. So as long as you put that approximation symbol in the first one, I don't want you to put it here because all you're saying is that 42 is equal to this amount. Okay? Let's move on. So midpoint is going to be this question. Let's always start off by finding our delta x, which is b minus a over my n, which we want 4 rectangles, which is going to give me 4 over 4. My delta x is 1 again. This question ends up being a little different. As I start writing out my x's according to my delta x, I have 1, 2, 3, 4, 5. Now that happens because, again, I only changed one x every time. But because I'm going to pick my height based off of the midpoint of the x, I'm not going to end up using these. I'm going to end up using the middle of 1 and 2, which is 1.5. I'm going to base my height off of the middle of 2 and 3, which is 2.5. I'm going to base my height off of the middle of 3 and 4, which is 3.5. And then the middle of 4 and 5, which is 4.5. And those are the x values that I'm going to pick my height off of. Okay, so if I plug in 1.5, I get 7.5, then here 8.5, 9.5, and 10.5. So this is already the height, right? If I'm drawing my rectangles go, here's the first, here's the second, here's the third, and here's the fourth. And then I'm picking these heights that are the actual middle point of these rectangles. Okay? So when I go to solve this one, my area, according to the midpoint, estimated, my delta x is 1, times, add up my y values, right? This is going to give me 36. Now for the trapezoid. Let's start by finding our delta x. b minus a over the number of intervals, which we said was going to be 4. My delta x is 1. Let's start by doing our chart. If I started at 1 and I'm moving a delta x, a change in x of 1, I'm only going to change one number at a time. Okay? Now remember, the whole point of trapezoid is I'm going to take the average of the heights. So I do need each of these heights. So I'm going to plug in all of these numbers into this equation, plus 6. And those are my y values. Okay? So these are my rectangles. My first one, my second one, my third one, and my fourth one. Okay, if they say 4 intervals, you should be able to draw 4 rectangles. Now my area, approximated according to my trapezoid. Okay, I do have a 1. And now the whole point of trapezoid is I'm going to take the average for my first rectangle of these two heights. So I have 7 plus 8 divided by 2, the average of those two heights. On to the next rectangle, the average of the two heights. On to the next one. And my last one, the average of those two heights. Notice that each of these are being divided by 2. So I can factor out a 1/2. If I factor out a 1/2, I am left with just these numerators. 7 plus 8. Remember what I told you would happen every time it's a triangle? See how the 8s repeat? Now how the 9s repeat? And now how the 10s repeat? And my 11 at the end. And I had my 7 at the beginning. Once you clean this up, you end up with 72 over 2, which gives me 36. All right. Last one. We haven't talked about this one yet. Let's talk about an inscribed rectangle. Okay? Bear with me. It's nowhere near as hard as you're probably thinking. Let's start with our delta x. Right? B minus a over the number of intervals. We had said at the beginning it was going to be 4. Once again, I know this seems like we're going through the motions and always getting 1, but these numbers could always change, okay? So my chart is going to move one number at a time because its delta x was 1. Now I'm going to plug these x values in to get my y values. I end up with 7, 4, 3, 4, 7. I want 4 rectangles. And now let's talk about what that word inscribed means. If it's inscribed, that means it's going to land inside, like underneath the function. So I'm going to show you this again. This rectangle, because it's underneath the function, is inscribed. This rectangle, because it landed above, is called a circumscribed rectangle. This one went over, so it's circumscribed. This one went over, circumscribed. This one is under, so it's inscribed, and this one is under, so it's inscribed. You're not going to see these asked much because an inscribed rectangle throughout the entire thing is always going to give you an underestimation. And circumscribed, being above all the time, is always going to give you an overestimation. Okay? But just to show you how the math works, if we want inscribed rectangles, we're going to pick the shorter, smaller y. If we want circumscribed rectangles being above, we're going to pick the bigger y. Okay? So out of this first rectangle, if I'm doing inscribed, I want the smaller y. You ask yourself, who's smaller, the 7 or the 4? My first number is a 4. Now for my second rectangle, who's smaller, 4 or 3? I'm picking the 3. From the next one, who's smaller, 3 or 4? I'm picking the 3 again. And from 4 and 7, I'm picking 4. So I'm not going to use the 7. I'm going to use the 4 once. For this rectangle, I'm using the 3. For this rectangle, I'm going to use the 3 again. And for this one, I'm going to use the 4. And I'm not going to end up using the 7. If this was a circumscribed rectangle, we'd be using, instead of the smaller number, just the bigger number. That'd be the only change. So my area, according to inscribed rectangles, estimated is my delta x, which is 1, times all of my heights added. I have 4 for my first one, 3 for my second, 3 for my third, and 4 for my fourth. I add that up and I get 14, which obviously, because it is an inscribed, is an underestimation.